Welcome to Lyons Township High School AP Physics. Today we have an example using work and energy, and there'll be a little bit of review in this as well. So I've got a whole bunch of data written up here, which you may want to copy down. So go ahead and pause the video and copy all this down. All right, you're good. All right, so we're lugging a crate. Got a mass, we're pulling it with some force, we'll call it P for pull, at some angle. There's a kinetic friction between the crate and the ground. We're going to drag it some distance d. At the beginning of the motion, the box is already moving, and we're going to ask you a whole bunch of questions. So here's your data. These are the numerical values for all those things I told you about. Things we're going to determine. We're going to figure out what's the net work done on the box by all the forces acting on it. What's the change in kinetic energy of the box? What's the final velocity of the box after we drug it 5 meters? And then we're going to discuss, just real briefly, is energy conserved and is mechanical energy conserved in this problem? Okay. So the first step in doing a problem like this is we have a problem that involves multiple forces. So if you are in Physics 1 at LT, you better know what the next step is, and that is to draw an FPD. All right. So we're going to draw 2 FPDs. I'm going to sketch what the forces are acting on the box and which way they point. So we'll do that first. So we've got the pull force going off at some angle. We have the weight of the box, which will be mg. We have the normal force acting on the box, the ground holding the box up. That is F sub n. And then we're dragging it along a rough surface, so there is friction. Friction will always be parallel to the surface. All right, so there's our 4 forces acting on the box. Now, we always split our forces up into components, and those components will be parallel to the motion and perpendicular to the motion. So for this case, parallel to the motion is this way, and perpendicular to the motion is that way. Okay, well, both mg and fn are perpendicular to the motion. We don't got to do anything of those. ff is parallel to the motion. We don't got to do anything of that. P is neither parallel nor perpendicular to the motion, so we do need to break it down into components. Now, I haven't put any numbers here yet. I will put numbers in the next diagram. So we'll redraw this. I'll draw it here. Okay. Oh, and I'll make a note, by the way. Will Fn equal mg? Hopefully you recognize that it will not equal mg. Next question, will Fn be more or less than mg? Well, hopefully you recognize that since P is pulling up some, Fn doesn't have to equal mg. It's going to be less than mg. In other words, the component of P pointing up and Fn together will equal mg, okay? Which we're going to do in this diagram here. So, having said that, I'll redraw mg. Redraw friction, redraw Fn. Okay, we have 2 components of P. We have the component that's horizontal. That will be P times, there's your angle, and you want the adjacent leg today, that's that. The adjacent leg will be cosine. So this will be P cosine of theta, but P also points up a little bit. So there's an upward component. I'll put that right next to Fn. And that component, that's the opposite leg in that triangle, so that'll be P sine of the angle, okay? Now, we can go ahead and determine these, okay? So if you take 200 cosine 30, you can try this out in your calculator, you should get 173 newtons, okay? I'm not going to label them all, but that's 173. mg, you take 50 times 9.8, you should get 490. Okay? P sine theta, no calculator on this one. You take 200 sine of 30. Well, sine of 30 is a half, so 200, half of that will be 100. So now look, this box is not accelerating up or down, so I know that these 2 forces together have to equal mg. So what plus 100 gives you 490? Well, Fn has got to be 390, which is indeed less than 490. Friction. Okay, so I'm going to do that calculation right here. Force of friction equals mu Fn, okay? Mu sub k Fn in this case, we got kinetic friction. And we have those numbers. Mu sub k is given as 0.3 in the problem, and Fn we just figured out. You got 390. You take 0.3 times 390, you get about 117 newtons. Okay, so that's, I mean, honestly, that's probably one of the hardest parts of the problem is figuring out all the forces and getting numbers for them. Okay, now to figure out, we haven't done any of this yet, but you have to be able to do this to get all this. Okay, so we'll start with network and so on. So there are several forces doing work in this problem. And actually, let me pull this back down a sec. Okay, but let's start with the forces that are not doing work. Okay, forces only do work if some component of that force is parallel to the motion. Well, in this problem, looking at this part, this FBD, mg will do no work because the motion is horizontal and mg is vertical. It's perpendicular. Fn will do no work because Fn is perpendicular to the motion. P will do some work, okay? And which component of P is going to be doing our work? Well, P cosine theta, because that is parallel to the motion. Also, what sign of work will P cosine theta do? Well, the motion is to the right and P cosine theta is to the right. Whenever the motion and the force are in the same direction, that force is doing positive work. It's adding energy to the box as you go. So this guy is going to do positive work. Friction is pointing the opposite way of the motion. So since friction is pointing this way, but our motion is to the right, friction is going to do negative work. It's going to suck energy away from our box, okay? So I will find the work done by each of those forces, okay? So the work done by P is P that's parallel to the motion times the distance, okay, which was given as 5 meters, okay? Well, this is simply P cosine theta times d, and we got these numbers. P cosine theta was 173, and d is 5, and you get positive, and I'll put a plus up here too. That's positive work. We just mentioned why. I got 865 when I did that in the calculator, and that would be joules. The work done by the force of friction will be negative the force of friction times d. And I just put a negative out front because I know that friction is pointing the opposite way of the motion and it's doing negative work. Now it's important to do that, by the way. So we get negative 117 times 5, and when I put that in my calculator, I got a negative 585. Okay, so those are the only two forces doing work. Now, I'll go ahead and mention the work done by the normal force is 0, and the work done by mg is 0. Those are 0 because both those forces are perpendicular to the motion of the box. They'll do no work. Okay. So, question, what's the net work done? Well, you've got 4 numbers. There's the work done by P. There's the work done by friction. There's the work done by normal force and the work done by gravity. To find your net work, net means sum. You just sum them up. So the net work done on the crate would be, let's see, 200, oh wait, no, I don't know, what do you get here? Let's see, let's try it out. Oh, 280. 280 joules. If you add this plus negative that, you get 280 joules. So that's the net work done on the crate. Now, the next question we asked up there is, what's the change in kinetic energy? Well, net work is the change in kinetic energy. And by the way, I'm just using a K for kinetic energy. Some of you might write KE, and that's absolutely fine. Okay? So that's equal to positive 280 joules. So what does that mean about our crate? What does that tell us about the crate? Well, that means the crate's speeding up. Okay? The crate is accelerating. If this number were negative, that means that the crate would have been slowing down. So by the way, before we figure out V final, we know that since the crate's speeding up, since the net work is positive, V final will be more than V naught. So V final better be bigger than 2 meters per second. So we'll see. All right, so the next thing you can do, there's a couple ways to do this. You can use conservation of energy equation if you want. So at the beginning, the box could have some kinetic energy. It could have some potential energy, and I'm using U for potential energy. Some of you may write PE, that's fine. Plus any work done by non-conservative forces equals the final kinetic energy plus the final potential energy. Well, there's no lifting of the box or anything, so there's no change in potential energy of the box. This term is this, okay? There's actually two terms that go in here. There's the work done by the person, which is positive 865, and there's the work done by friction, which is negative 585. You add those two together, that's the total non-conservative work done. KE naught, we can get a number for that, right? We know the starting velocity of the box is 2 meters per second. We know its mass, so I'll write that down here. K naught is 1/2 mv naught squared, which is 1/2 times m was 50, and v was 2, and you got to square that, and no calculator necessary there, you get 100 joules, okay? So we know this is 100, so I'll kind of put this here. We know this is 100. We know the work non-conservative is 280. That's got to equal the final kinetic energy, which is, without a calculator, hopefully, you see that's 380 joules, okay? So the final kinetic energy of the box is 380 joules. Now to find the final velocity of the box, you're going to use that equation again, but now this is going to be V final. This is going to be kinetic energy final. If you do a little algebra on this and solve for V, you get V final equals the square root of 2K over M, which is the square root of 2 times 380 over 50. And if you plug and chug that in your calculator, you get 3.9 meters per second. So the box is going almost double the speed it was going at the beginning of the problem. Okay. Now, questions that College Board will ask on an AP exam. Okay, very good questions. Number one, is energy conserved in this problem? Well, energy is basically always conserved, okay? If you look at mass energy equivalency, then energy is always conserved. So, in this problem, energy is conserved. Now, what does that mean? That means that this side is equal to this side. Well, that's always the case because you got an equal sign there, okay? Now, the other question is mechanical energy conserved? Okay, that's a different question. Mechanical energy, so I'll abbreviate that ME, mechanical energy. That's defined as the sum of your kinetic energy plus your potential energy. Is that the same before and after the motion? Well, before the motion, we had 100 joules of kinetic and no potential. After the motion, we have 380 joules of kinetic and no potential. Is 100 the same as 380? Clearly not, okay? So mechanical energy was not conserved in this problem. As a matter of fact, we gained mechanical energy. So that's another question they might ask. Another question they might ask about these numbers. They might say, hey, is the work done by the student, the person doing the pulling up there, is that work more, less, or equal to the net work done on the box? So let's repeat that question now. Is the work done by the student more than, less than, or equal to the net work done on the box? Well, if you look at the numbers, let's do that first. Here's the work done by the student. Here's the net work done on the box. Clearly, the work done by the student is more than the net work done on the box. Now, they might ask you to explain why. Why is the work done by the student more than the net work done on the box? Well, the reason why the work done by the student is more than the net work done on the box is because you got friction. Friction is taking energy away from the box. Sure, the student gave the box 385 joules of energy. Friction took 585 joules of that away. You can even go further. They might ask you to say, where did that 585 joules go? Well, when that crate is sliding across the floor, friction's doing negative work, sucking energy out of that box, and it's turning it into, you guessed it, is turning it into heat or thermal energy, okay? You're making the molecules in the ground and in the box move a little quicker. That's what temperature is. It's motion in the molecules. That is, you're changing mechanical energy into thermal energy. So that's where that non-conservative work is coming from in this case. So those are the kinds of questions they're going to ask you on an AP exam, not only to calculate numbers, but to be able to explain what's going on, where the energy is going. So I hope that was helpful, and thank you very much.